This is the Empower Podcast. Released March 13th, 2022. Episode 581. Real-Time Operating Systems with Brian Amos. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And this is Brian Amos, author of Hands-On RTOS with Microcontrollers.
Hey, Brian. How are you?
Doing well. How about you, Chris?
I'm good. I first heard about your book, I believe, from Philip from Embedded Artistry.
Yeah.
And then I read it, and I was getting into RTOSes, and it's a really good book. So thanks for being on the show today. I'm excited to ask you all the dumb questions that I had as I was reading the book.
My pleasure. You're definitely in the target audience for the book. So
people who are done with RTOSes, all right, yeah, that's what I expected.
No, hardware engineers with prior programming experience, or have a familiarity with hardware. That's it.
Yeah. You know, I mean, this all kind of started coming up when I was doing some NRF52 projects, and I was kind of poking around NRF52 or the NRF5 SDK, and there's a bunch of free RTOS stuff on there, and I was, thinking I could do some Bluetooth stuff using their binary blob, but there was other examples using free RTOS, and a bunch of people had used free RTOS, and so I started exploring it, and I think that kind of led me down the path towards this stuff. And I remember I talked to Alvaro Prieto, who's one of the co-hosts of the Reverse Engineer podcast, and he's a big free RTOS fan as well. And I think he had also maybe mentioned the book, but just kind of like as a starting point, I was like, all right, I need to learn RTOSes, and yeah. I was kind of just hunting around for info. Is that a common thing that you see? Is people just saying, today's the day I need to start learning RTOSes?
I don't really get too much. Like, people aren't coming to me saying, "Oh, how do I get started?
How do I RTOS?"
Yeah, how do I? What is this whole RTOS thing? Usually, I wind up talking to people that have been programming for a while, and inevitably, they don't really know what an RTOS is or why they would want to use one.
Mm-hmm.
So it's not even like, oh, how do I get started in this? How do I dive in? It's more like, well, I have my C compiler, and what else do I need? Right. And it's like there are lots of tools out there that can help you.
Yeah. Yeah. For people that are like thinking about an RTOS, I feel like the first thing is like, well, would a state machine do what you're really needing? It's like, if so, and it's like really small, that might be the best option.
Mm-hmm.
It's like, but then I had been asking some people about like, oh, well, should I just start from the premise of like, just go straight to it. I'm going to have a real-time operating system instead of a state machine. And some people said, yeah, that's how I prefer to do it.
Yeah. It's funny because a lot of the projects that I've done, some of them are inherited, right? So you already have a code base and you need to add some features to it. And other times you have an idea of what you're going to be doing, and it's more well-defined. You can kind of bound it a little bit better. And that if you know ahead of time,
yep,
minimum requirements and then desirements after, that MVP is done, then you can usually get a pretty good idea. But
okay. So say we got a greenfield project, not like a I say brownfield for inherited, already built, greenfield for clean sheet of paper.
Yep.
Give us an example of a project that you've either seen or tell me about a time. This feels like an interview. Tell me about a time. But like, what is a good example of like, you're probably going to want an RTOS, or maybe not. You don't have to care about it. Do you have those in your head?
Yeah. So anything if you have a user interface, almost definitely, because, especially like a GUI, an onboard GUI or something like that. Anything with extensive communications capability for sure. So network connectivity, USB, tons and tons of SPI, UART.
Anything with a stack in the name.
Yeah. Lots of, especially like third-party stacks that might be really bloated. If you can you can use an RTOS to segment a lot of that what I'm going to say lower priority stuff, and then write really efficient event-driven code that's really, really close to the hardware. We're talking ISRs, all that kind of stuff, right? And
Mm.
so you push off all of the third-party stuff, push it into its own task, give it a nice low priority, and then any of your higher priority things that deal more directly with time-sensitive hardware, you kind of do that like under the hood, right? Actually below the RTOS. So you don't even have to interact with
Yeah.
the RTOS if you don't, unless you have a reason to.
That's kind of confusing too, because low priority is it's like low priority. It's like golf, right? It's like if you're bad at golf, you have a high score.
Mm-hmm.
If you have a low priority in an RTOS system, you have a high priority score. Isn't that right? Or is that, have I have that backwards?
Well, that's like, so the Cortex, I'm not talking about Cortex M
Ah,
ISR
okay.
rankings here. I
Mm-hmm.
literally mean low priority. So if you've got
Mm-hmm.
something, let's say, all right, let's say that I have like a control system, right? So I have a closed loop control system where I'm reading sensor data, and I want to control the position of, let's say, a motor, right? So I'm going to read in data from a sensor, and I'm going to control some sort of an
Mm.
actuator,
Okay.
and you have to do that in a tight loop. So we'll say that's high priority, right? Because that's like the main purpose of this system is to
Yeah.
control this motor, right? It's a servo control
Yeah.
system. And then let's say that you also have a front panel for changing the set point or whatever, right, of
Okay.
this positioning system. So I'm going to argue that the front panel is a much, much lower priority because it's only dealing with user input
Right. Right.
than the actual positioning of the motor, right? So, you like UX guys are going to be screaming, oh, I can't have glitchy
We need it
UIs,
to
all
be
this.
responsive.
Yeah. It's like, okay, well, you can have your responsive UI and that's fine. But the position of this thing is really kind of the
But if we chop
important.
someone's finger off, we're gonna be in trouble.
Yeah, exactly. So the nice part about, if you have this, crazy, let's say you've got animations on the UI, a whole bunch of unnecessary crap that's like standard these days, right? And expected. You can kind of you push the priority of all that junk down, and then you operate a higher priority for all the stuff that actually matters. So it's
Yeah.
great for prioritization. It's definitely not a magic bullet there by any means, but
Yeah.
yeah. So that's one case. And let's say that this thing has also got some crazy IoT stack on it or whatever, and it's
IoT.
talking,
Those
yeah,
guys.
talking to the
Come
cloud or
on.
whatever, right? Some horribly bloated piece of software that has
Mhm.
been written by an entire team, and you bring that in, push that to a low priority too, right? And then it's just focus
You can
on the real
you can
time
talk to the
stuff that
network when I
matters.
tell you you can talk to the network.
Exactly. Yes. Yeah. And you want to do that stuff in the background when you have time. That's perfectly okay. But let me just
Yeah.
make sure that I actually do my primary function first.
Yeah. Yep.
So
Yep.
anytime multitasking is important, and you have a bunch of low.
Yeah, so the multitasking, a lot of different kind of once in a while things happening. I kind of I remember coming at this problem from like thinking about it from more of a like an embedded Linux perspective, and thinking like I wouldn't want something trying to get an update on a web page
Yep.
while I'm waiting on, data coming back from like a spy sensor or something like that.
Exactly.
And
Yes.
that would be bad. And in a full operating system like Linux does that sort of thing at a different level. So could you differentiate then for people real-time operating system from a full operating system?
Yeah. So the book was based off of free RTOS. I mean, a lot of the microcontroller targeted RTOSs are very, very similar, but with free RTOS is really just, it's pretty much just a scheduler and like some really basic things like queues, semaphores, task notifications, that kind of stuff. So you don't have any libraries. There isn't a whole lot of stuff now that Amazon acquired them. They're starting to add a bunch of that stuff, but at its core, it's really just a scheduling kernel, as opposed to Linux, which is, of course, a full blown operating system, and you can bring in libraries and drivers and all that kind of stuff. You
Mm-hmm.
don't really
Yep.
get any of that stuff. Different RTOSs, you can purchase them, You can purchase modules sometimes, right, depending on the vendor and that sort of a thing. But it's really just super pared down. And what it's really, really good at is bounding things based off of time. So if you say, oh, in your example with the, waiting on data coming back from a spy sensor while you're trying to load a web page, right? The data coming back from that spy sensor, you could actually bound that and say, hey, I expect data back from this sensor within 10 milliseconds. And if it doesn't come back, if it doesn't complete in this amount of time, or if I can't acquire a mutex or a semaphore or whatever you're using to access this peripheral in X number of milliseconds, then bail out and do something, right? So all those kinds of timeouts are built into pretty much all the calls, and there's always, you're always thinking about, okay, after this thing goes wrong and there's no sensor on the other end, what happens, right? So you don't get into, and you can put in infinite delays if you really want to.
Sure.
It lets you, but you're always thinking about what happens if something goes wrong. So it kind of gets you into that mindset, and that's something pretty different as well. I mean, for systems programming, I suppose you have exceptions and that kind of stuff, but
yeah. So the thing that I always hear about with like OS versus R2OS is something about memory management is one thing. Is that kind of or is it just more the build out as well? Because like the other thing, my other reference point here is that I've been doing a lot of Zephyr stuff poorly. I'm learning a lot of Zephyr stuff, I suppose I should say. and that's kind of like, it's not just the kernel. It's not just, there's like other stuff kind of already there and monolithic and built in. And it's more like starting from the middle and saying like, okay, you've already got a lot of stuff in this huge package and you can pare it down. Yep. But most of it, what you're getting, you kind of get it all there first. Whereas like you're saying with FreeRTOS, it's kind of like, well, you start from the bottom and you build up. You can bolt stuff on and put things together, but you start with the assumption that there's not much there. And then I think Linux side is like,
and as far as memory management goes, like you can do as much or as little as you want. So there are ways of creating entire projects, and it's not just FreeRTOS, but with a lot of RTOSs that are purely statically allocated. So there is no heap, right? So there is no penalty, there is no malloc, there is no new, those kinds of projects exist. And you can get really, really good at predicting how long things are going to take when you're not using a heap, because it's just machine cycles at that point. You're not searching for a spot to put this variable in memory, right? And then, even if you use the FreeRTOS heap, if you prescribe to the notion that you create tasks and then they just run forever, like their own little state machine, each task is basically a state machine, right? So if let's say you create 5 tasks and you want to have the ability to do dynamic allocation, you can use the heap, but the only time that so you would set up a stack for each one of those tasks, and at the beginning, like, right at the beginning of main before you start the scheduler, and you don't have to touch those. So as long as you go out and you acquire the memory that you need, you have the memory, there is no more dynamic allocation, and you're good to go.
Yeah. So, and you get what you get then, right? You're just doing that. You're just using the memory you have at the beginning.
Yeah. So, right. If you're like, okay, well, this is a pretty, this is a very small task. It can probably get away with 512 bytes of stack space or whatever. Then the stack for that task is set to 512 bytes. You never have to ask for more, and right, that's it. And that task will do whatever it needs to do. And as long as you never go above 512 bytes, you're golden.
Right.
Just like overrunning arrays, bad things can and do happen.
Yeah.
But it has some hooks in there to detect that kind of stuff as well.
Got it. So like the thing I want to kind of offset there is like like I said, my reference point is kind of Zephyr. It's kind of like in the middle somewhere. free RTOS and other kind of, and especially like bespoke RTOSes, because you talk about that in the book a little bit as well. And that's kind of bottom up. You're kind of building each thing up. And then when Jay Carlson was on the show talking about embedded Linux development, it's one thing he talked about was like, well, you're going to end up reading a lot of code, but not writing a lot of code. So it seems like the free RTOS, you are writing a lot of code, but you are crafting it how you want it to be. So it is that bottom up methodology.
Yeah, very much so. And it's API is pretty minimal, so you're not really. I mean, if you're bringing in the exception, of course, is as soon as you start bringing in third-party libraries, you're reading a ton of code, right? Or maybe documentation or whatever.
Right. Yep. Yeah, you want to know how you can interact with their APIs and what are all the gotchas from that sort of thing, and what you might want to draw out of them, right?
Yes, exactly. Yeah.
Yeah. So one thing I really liked about your book was, because it is that bottom up methodology, I feel like most books start a little bit too. Most of the RTOS books that I've done, they immediately want to talk about just like only semaphores and only mute. Like I remember John LaBrosse's book about Micrim and Micro COS 2. Very good book, very good reference. But man, it just wants to talk about mutexes, and I'm just like, I don't know what the hell you're talking about right now.
Yep. Yeah, that's why all the diagrams were at the beginning without any code around them. Like little flags.
Yeah.
Here's a semaphore.
That's really useful.
Yeah. That's because the first time that I used an RTOS, I drew out all that crap.
Yeah, that's great.
Like, I haven't seen this stuff since school. I've got to go back and get a refresher here.
And I think that's super important, like to be able to do that sort of thing. And I guess one of the things that I didn't realize, because I got so kind of stuck on that other stuff, is, and I'm probably going to say this wrong now, but like the idea of an RTOS having the segmented memory, like you said, that 512 bytes, it's segmented, but then it's like it's doing its own thing. The task, or how to say this? It's like you have these side by side neighbors. They're like apartments of memory, right?
Yes.
And they're like side by side, and they're living next to one another. But they are these stacks that live next to each other as well, right? They act like a stack, but they're all.
Well, they are a stack. Each task has its own stack, right? And that stack is only used by the task. And then you also
that was completely new knowledge to me. Like I did not understand that at all about it prior to your book. So that alone was the price of admission for me. That was really worth it. That was awesome.
Good. Yeah, and then there's inter-task communication between the tasks, right? Yeah. And that's where you get things like, okay, well, I can have a queue, and that queue, let's say that's a global, right? It doesn't live on either of the two stacks. It's effectively a global variable that's,
Can we make like a Sesame Street style analogy here or something? That would be very useful for me. Where like a queue is like there's like mailboxes, and would be like, I don't know, like a water slide between them or something.
Yeah. And I think I have to go. Let's see, understanding RTOS tasks. If there are actually some really simple diagrams that explain this stuff at the beginning.
Great. And I have the same PDF that Brian has open, so we'll be able to say, we'll try and backdate it to what chapter and stuff like that, but we'll probably talk about page numbers here from the PDF. So if you're on my Kindle version is very different, so that's why we're looking at the PDF.
Yeah, so if you look at the page numbers on the bottom of each page on that PDF are actually like the same page numbers as the book. The book is just like a printed version.
Oh, great. Oh, like you mean like the paper book?
The actual, the dead tree thing.
No, I don't. Yeah, I'm a Kindle guy personally.
Yeah, there were quite a few complaints about the Kindle version.
Oh yeah.
Well, the publisher decided it was a good idea not to put chapter numbers.
Yeah,
like there are no chapter numbers anywhere. It's crazy.
Yep. Details.
Yeah.
Details.
Yeah. So on, let's see. Yeah. So in chapter 3, right, you have these queues, and there are some super simple. They're just boxes. If you have a queue of length 4, right? You can think of that as 4 bins, and you put something into the bin, and then when you take it out the other end, that's it. It's just like a conveyor belt, right? If you want to think of it that way.
Yeah.
It's
Or how
But
about if we had two tiny fiefdoms of memory, then it would be like the security checkpoint between the two, right? Because you get in line to check
yeah,
to get through the
exactly.
checkpoint,
Right. Yeah. And
right?
then those,
Yeah.
the two guards that are, staring at each other through the two fiefdoms, they're making sure that one task doesn't step on the data of another task, right? So they're
Yeah. Okay. All right.
guarding
Yeah.
between
See,
tasks, if you want to go with that.
we're building a world here as we speak, folks. We moved away from Sesame Street pretty fast. I'm pretty sure Sesame Street doesn't have guards. It's not like the Count being like one
I,
refugee coming from one
between
space to
the,
another.
I mean, you need Oscar the Grouch in there too.
Yeah, yeah, he would definitely be. Yeah,
The
he's a
count
trash
can
collector, right?
totally be in there. He could be like taking care of counting semaphores,
Yeah,
and
yeah.
then
He'd be like the Tick, right? I
I'm
mean, he'd
not.
be like
I guess Oscar the Grouch should be like config assert. So
okay.
in free RTOS, there's whenever you do something wrong, like
Uh-huh.
there's this notion of Isr safe functions, right? And if you
Mhm.
call if let's say you try to add to a queue with like the normal API from inside of an ISR, then you get a config assert. So it's an assert that fails. It's like,
Mm.
whoa, this is within an interrupt context. So
So
that
it's
could be
like
Oscar.
grouchy.
Yeah,
Yeah,
it's
yeah.
totally
That's
grouchy.
good.
Yeah.
Yep. Okay. So that's how you get from one task to another. And so the task is kind of like
That's one of the ways.
is that like the smallest block of memory?
Yeah, well, I
Mm.
mean, you have semaphores, which are very, very tiny.
Mhm.
I imagine in FreeRTOS, they kind of implement everything under the hood as a queue,
Mhm.
which is interesting I think it saves ROM space, but some people complain that there are faster ways of doing that. But
Mm.
yeah, so I mean, you can have a queue of length one, you can have a binary semaphore, right? But the only time that you're really creating these things that are running in concurrently are when you're creating a task.
Hmm. Yeah, okay. So now say we have a system with maybe we should make up a fake example here.
Yeah.
So we have a task that's
What's your system doing? What do you want your
let's
system to
call
do?
it a how about a ventilator, right? There's all that open ventilator stuff. So it's like there's a task that's measuring air pressure, there's a task that's actuating a pump, there's a task that's updating a screen about the status of the pump,
Yep.
and there's a task that's reporting it to the internet or something like that. Even though that would be a huge task, we're gonna make it a magic task. How about that?
Sure. Yeah. Yeah. So, you're probably going to have, I would say, like a task that's taking care of reading the life critical kind of stuff, right? So that gets the highest priority in the system. So if it has any work to do at all, then it will run no matter what, right? And in the case of a
Mm-hmm.
ventilator, you would definitely, that's priority number one. You don't really need to, like tweet the number of breaths the
Right.
ventilator is
PSI. Yeah.
provided to
Right. Yeah.
yeah, you don't care about any of that kind of stuff. And the other important thing for that high priority critical task is that it's it can't be waiting on any shared resources from any of the other tasks. So you really want that to be pushing information out,
Yeah.
right? So
Ah. Okay.
you don't want to get into a situation where there's this crazy big block of shared memory and you're waiting on a mutex for something to update. You just want that, you
Okay.
want that critical task to be continuously running. And then when it has information to disperse to the other part of the system, it would do that probably through a queue.
Yeah.
Would be a reasonable thing to do.
Yeah. So the other thing that kind of that this your book opened up for me is like, okay, so now you have something that's just it's a task, it's just reading a sensor. And that just looks basically it looks like if you just had a single function program that was just like spy read, and then it's just a loop basically. But instead of like and correct me if I'm wrong here, but instead of saying like wait 5,000 milliseconds, it says I'm going to go to sleep for 5,000 milliseconds or whatever the timing is.
You can have super, super fine grained tasks like that. More often,
Mm-hmm.
they wind up getting segmented more along the lines of like a group of responsibilities, you know?
Okay. All right. So would it be like sensor package? So it'd be like,
Yeah, so I would, I mean, and again, this is getting into design decisions, right? But typically, if I'm creating tasks, then they're going to have, it'll be a task. Let's say the ventilator example, right? It's going to be the measurement of your PSI or whatever it is going to be happening. You're going to be taking that measurement in. You're going to be controlling your actuator. All of that is going to be in a single task. You wouldn't necessarily need like two tasks, one for the
oh,
sensor,
interesting.
one for the actuator, right? So you're kind of grouping stuff in like tasks and or like functionality, right? So then you push
Got
all
it.
your IoT stuff and that stack out onto a different lower priority task, probably in that example.
So when do you make? I mean, you mentioned design decisions, but like when do you construct that? I would imagine that there would be problems if you like. Then what if you need to go reconstruct something later? Is it tough to do that sort of thing and be like, oh, actually, no, now we need to have the sensor package talk over a queue to the motor instead
Oh,
of
it's just
having them
like
in the
anything
same task.
else. It depends on how much spaghetti you've created
Uh-huh.
first, right?
Imagine infinite spaghetti for me. Uh,
Yeah, so really, the best thing to do is just to you sketch it out on a napkin and say, hey, I have requirements A, B, and C to take care of.
hmm
How am I going to accomplish these things? What needs to happen concurrently to the other stuff? Each
hmm
thing that's got
Yep.
to happen, seemingly in parallel, would get its own task. If you have some long running stuff that's low priority, that gets its own task. If you have some higher priority things that need to happen with tight time constraints, they either need to go into ISRs and just deal with them below any of the RTOS stuff. So in the ISR context, that's going to run no matter what, right? So
And ISR is interrupt service routine for people that are hardware focused like me.
yes, yep, yeah. So all of your interrupts,
Yep.
you're going to configure those so that you're almost always so that your scheduler interrupt is a lower priority than any of your critical interrupts, right? So
Right.
if you have real-time sensor data getting streamed back from something, right? So let's say that that pressure sensor on the ventilator is streaming data, then you would make that a higher priority, and you would always go out and read that no matter what, right? And then
Yep.
you can squirrel that data away, and then post a semaphore whenever you have enough of it and it's time to do something with it. And then at that
Yeah.
point, the scheduler takes over, and you start having RTOS tasks kind of spin up.
Yeah. I think that was another thing that I didn't quite understand is that you can, so like if you're designing a system now, and I had been, kind of in the bare metal working with interrupts and getting used to that. And then it was like, well, if you're in an RTOS now, you actually don't ever need to use an actual hardware interrupt anymore because basically an interrupt is
Got to be
built
careful
in.
there. You have to be very, very
Okay.
careful there. You
Why is that?
you can program like that, but
Yeah,
uh,
not as like a wood, but like because yeah, I mean a lot of the sensors I use they have a pin that goes high when they're done with it, when they have a reading ready. So I would
yes,
want to use that, but
right.
in the event I didn't have that, I just had like really silly simple just analog sensors, and it was just like this interface into an old analog system or something. In theory, I don't need to have physical hardware interrupts.
Yeah, I mean, you can if you're so I have to be a little bit careful here, right? So Dep depending on how fast
Someone in a future design meeting and be like, "Well, Brian, but on the amp hour you said,
So, I mean, how fast are your sensors being read, right?
yeah." I mean,
Like that's
I'm not going to hold you to this here. I'm just saying this was my epiphany about it, where I had kind of always thought it was like the two choices were, well, you can have an interrupt driven system where you have these sensors and or
oh, I see what you're saying.
buttons that are
Yes. Yeah,
talking
absolutely.
back, or you're on like just a loop and you're saying, well, I'm going to poll everything.
Right.
And the epiphany here was like, oh, well, there's much better options in the middle, which
Well,
is
but the
something like
tricky
this.
thing, the one thing to keep in mind is, yes, you can write polling routines inside of a task in an RTOS, right? That's not a
Mm-hmm.
that's perfectly okay to do. But at that point, you've still written a polling routine,
Mm-hmm.
and your CPU still needs to go out and check whatever it's pulling at some interval, right? So you're
Yes. Right.
still
Right.
using CPU cycles depending on how fast you want to check that thing.
Mm-hmm.
If you can manage to design your hardware in such a way that it goes into an interrupt pin, or it starts communicating to a UART, and your UART peripheral has, or USART SPI, whatever it is, right? Some sort of serial peripheral has interrupts, then those interrupts could be activated. They can bring in a meaningful amount of data from the sensor, and then you can signal a task to wake up and say, hey, I've got some useful data, rather than that task spending time pulling this
Yeah.
thing repeatedly.
Yep. Yep.
So you can wind
Yep.
up with more scalable systems that have better response times if you avoid almost all the pulling possible. Now, of
Yeah.
course,
Polling
with really
bad.
high, pretty much, right? Like, and that
Yeah.
also
Yeah.
holds true for low power designs too. So the more things that you can have event driven in a low power design, the better, because the one thing that you kind of get for free, depending on which port of FreeRTOS you're using, some RTOSs, FreeRTOS is one of them, where they have a tickless mode. And so, like normally an RTOS, it has to keep track of time, right? And
Yep.
just
Another thing that I learned from your book, yes. People are
yeah,
getting a good feeling for just how little I understood about
it
it prior to this.
it's a very time is very important in a real time system, as it
Yeah,
turns
that's
out.
right. Yeah.
Yeah, so if you have a fully event driven system and it needs to be low power, and you need reasonable, like, let's say you want like millisecond time resolution for whatever reason, right? You really don't want your processor waking up from an interrupt every millisecond. That would be,
Right. The
that's
battery killer.
yeah, that'd be terrible. So they have modes. If you, again, you try and avoid the pulling route as much as possible, create everything to be event driven, and you can go into a tickless mode where if you have something to do, let's say once a week, and you're using hardware that has the capability with a real-time clock with an alarm,
Mm-hmm. Yep.
you can set everything up so that the whole chip gets powered down except for that RTC. It wakes up in a week, and then it's time to do whatever you need to do. Then it goes right back to sleep again. And,
Mm-hmm.
there's no CPU intervention necessary, between that time. Obviously, at that point you start talking about clock drift and that kind of stuff. But,
Mm-hmm.
that's where crystals versus RC oscillators start to become kind of
Yeah.
important for your RTC stuff. But
Yeah. I'm just surprised that I didn't get into this sooner, I guess. I mean, like, I should say get into this. I mean, read about it sooner. I don't know. How did you learn all this stuff? I mean, where did this all come from?
I remember, I'm not sure how okay. So the first time, my first exposure to, it was actually like an anti-RTOS. So I was working for a company, and we were developing a vibration monitoring sensor that was living on a mesh network. And
Okay.
so it was like, a mesh network, mesh wireless network, right? And this thing was supposed to wake up every once in a while and capture a waveform and then send it back to wherever. And some senior engineer had decided that, oh, there's this thing called a Telos module made by a company. This is back in, oh geez, probably like 2007, 2008 or so. And
Mm-hmm.
there's this Telos module. It was developed using this operating system called TinyOS, using a language called NESC. And so, a whole bunch of really obscure
Yeah,
stuff.
this is sounding good. Yeah, yeah, yeah.
So anyway, that was like, well, what the heck is this? Well, it's this little operating system. It's like an anti real time operating system. It's like, what the hell does that mean? Well, it basically tries not to do anything.
Bullet time. It's bullet time.
It's like it tries to push off as much as it can to do later so that it doesn't need to wake up, because that costs power. We don't want to do that.
It's like a sleepy time. Sleepy time.
That's exactly what it was. So they would batch up these processes. So you had all the interrupt level stuff, right? And then you would just effectively like post it to a queue, and then at a certain schedule, and the schedule could be like at 1 hertz or once every 5 seconds or whatever, the processor would wake up and it would chug through all the stuff that it had to do, and whatever those kinds of tasks needed to have their stuff done. And she's like, okay, here, I'm good. I have taken care of all of my duties. I'm going back to sleep for another 5 seconds or whatever that was. But that was my first exposure to it. So I was like, okay, there is such a thing as, like an operating system. And this is on MSP 430s.
Oh, so already pretty low power to start with, huh?
Yeah, so they're low power to start with. And these are like little 16-bit microcontrollers that had, I don't know, I want to say that the code size of that thing was like 14 kilobytes. So it was like, okay, this stuff doesn't need to be super, have super high-end microcontrollers or any of that kind of stuff. But yeah, so that was my first exposure to an operating system running on a microcontroller. And then later, we found out, I think it was like the other big one around then, I want to say Kentucky, but I'm not real sure. I don't think that lasted very long. And TinyOS kind of went by the wayside because they figured out that NestC wasn't a great, they were writing the operating system in and all the modules. NestC was like a really cool combination of structural VHDL and C. So it was very, very modular. And I wound up, they kind of infected me with their design methodology, because they would have these hardware presentation layers at the very, very bottom. And the job of an HPL was to expose like all the registers of a given chip, right? So you had access to absolutely everything the thing did. And then above that, you have, like this hardware abstraction layer. And the goal of the hardware abstraction layer was that you provide, let's say you have, like an ADC or something like that. Your hardware abstraction layer just provides like a single function, maybe, or like read ADC, and you get back
like ADC
a
read
number.
Yep.
Yeah, and that's it.
Yep.
But the cool part about that design methodology, in combination with this really cool structural VHDL kind of like routing stuff that they had, was that your code was immediately portable. And it didn't matter what processor it was running on. It didn't matter, the underlying IC that you were using, as long as you had written all that stuff, then the top level code existed and it was there, and you were guaranteed that it was going to work.
So when you port to a new chip, you just have to rewrite the VHDL-ish piece.
Yeah. So like if you have the same chip in 2 different boards, and let's say you move some GPIO lines around or something like that, then in that case you would like rewrite your routes and all that kind of stuff with a VHDL-ish thing. And then if you moved processors, then you would need to, like rewrite the routines that access GPIO registers and the stuff that accessed your peripherals, right? Like timer peripherals, serial peripherals, that kind of stuff. But yeah, so, and I've fully adopted that approach, and it served me quite well over the years.
Yeah, totally.
To the point where you can, using that level of abstraction, you can very easily write drivers for an IC and have them map across, chips, boards, architectures, doesn't matter. So it pays dividends in the long run to architect things properly, with decent abstraction.
Yeah, and like for testing then too, I'm sure that makes it easier for that as well.
Yeah, well, that's the funny part. So I found out about, things like test-driven development and all that much later. And, like I remember reading James Grenning's book, TDD with Embedded C, or I forget the title of it exactly, but test-driven development with Embedded C. I think I was like, man, all of my code is like super easy to test because it uses these well-defined interfaces. What do you know?
Yeah. Right. Versus like, I'm sure the code that I write, which is like, it's all in one file.
Yeah, all in one
It's yeah.
file,
That's
almost
bad. That's bad if you don't know,
exclusively
folks.
uses registers directly with,
Yep. Yeah.
got to
Bit
do the
masking.
bitwise math to to get access to anything.
Yeah. Yep.
Yeah, so multiple files is good.
Yep.
Giving names to the bits is also good. Long strings, like especially now with
Yeah. Human
32-bit
readable. Yep.
processors,
Yep.
long strings of binary is not favored.
Yeah. So at some point, I'm sure you've had the thought, I should just write my own real-time operating system, because
Never.
it feels
Nope.
like that's
Nope.
really
Nope.
okay. It feels like
Got no
the other
desire.
reading that I've done around this
I
was
am a
from Jack
user.
Gansel, and it's like it was like yeah, the number one RTOS out there is custom.
Yeah, and like at some point, if a program becomes sufficiently complicated, you're kind of forced into it, right? Because you have some routine that's chugging through a complex math calculation or whatever, right? And in the middle of that, you need to check to see if your UART's buffer is overflowing or whatever. So you wind up with all these
Yeah.
reads, these unrelated things sprinkled throughout this long running process. And yeah, no, I have no desire to write to roll my own RTOS. I'm very happy and grateful that other people are capable of.
That's great.
Yeah,
Okay. All right.
yeah.
I thought I was gonna trap you on that one, Brian. You passed the test.
No. It's people
And
much smarter
actually, I
than
would
me.
like to announce my new Brian Artos.
No.
Announced here in the Empire.
Yeah, I almost accidentally recreated portions of gRPC and for a project, and I kicked myself. I just didn't know about it. But,
yeah, no, that's
no.
good to. I mean, that's what it kind of comes down to for a lot of this stuff. Is like I don't know when I was in the hardware side for a long time, and I'm trying to learn more of this stuff, but I just don't know when I would have learned this. I'm sure some people learn this in school. I guess I don't
I mean,
know.
I had I have a computer engineering degree, right? So it's like a combination of hardware and software. So I focused on embedded systems in college, and there was an operating systems course, and I took it.
Was it meant for embedded operating system?
No,
Like or
no, it wasn't. Everything was it was all Linux.
yeah, it's like for writing Linux or Windows, right?
Yeah, it was it was basically a systems programming course, more or less, and it was just they taught you the basics of things, and that was that. But yeah, I didn't really see a whole lot of utility for it until until you have that first project where it's like, man, this is a little bit more complicated to do in just a super loop. So
yes, right. Yeah, and again, you would cross that threshold. You would so say you had a super loop project, and then you were like, oh, this is not going to be good. When do you pull the trigger? When should people listening, I suppose, is the real thing, and I guess including me. When should people make that, like, just bear down and make the switch?
well, the first time you converting stuff can be surprisingly difficult, especially when you're new. Converting like a super loop program into, if you're the original author of it, then you at least know about most of the stuff that you haven't. Like, okay, I know that this system requirement runs, and it's like I've got requirements ABC, and I know that all of those things exist. So then you say, okay, well, can I make requirement A into a task, requirement B into a task, requirement C? So it's really, if you find yourself sprinkling in calls that check on unrelated processes in the middle of a long running process, right? Like let's say you have a block of data that you need to do some math on, and
Okay.
so there's a loop, and you find yourself adding like, oh, every 100 iterations of this loop, I need to go check on the UART to make sure that I don't get a buffer overflow and I don't drop characters. Like at that point, that long
Yeah.
running
Yeah.
that long running algorithm should probably be in its own task, and there should be a different way of accessing the data and making sure that the UART, because the UART ISR isn't really, it's not really like a big deal necessarily, or maybe it is, and you actually need to break out of that long running task and go service that thing, that frame that just came across your serial line or whatever, right? It could be an abort, right? Oh, I've got this calculation that takes 30 seconds to do, and you could just imagine someone like hitting a push button, like, oh, stop it, stop. So attach the interrupt to the push button to a semaphore, and yank that
Yep.
task.
Yep.
But
okay, so let's go back to the ventilator example. The one thing I wanted to ask about that is, so you have this super high priority task, like keeping someone alive. Why isn't that always just running?
I mean, what's it doing, right? So does
I
it
guess
ever have
when I hear something like high priority, I just think like, well, that's always going to be, that's the highest priority. It's always running. So is that not the case?
Well, if
I'm setting you up for a dunk here, if you couldn't tell, this is very obviously not the case.
yeah, so it is if it's always running if it has something to do.
Got it.
But the minute that your high priority task needs to wait on something, like let's say it's set up to, I mean, I don't know anything about ventilators, but let's say it's set up
I don't either.
to operate. Say it's set up to operate at, like, I don't know, 20 hertz, 100 hertz, whatever it is. And it's going to evaluate
like human scale stuff.
Right.
Right.
It's not super fast. And you want to run this control algorithm for the ventilator at a rate of 100 hertz. Well, you're either, you're probably going to set it up so that you have like streaming data coming back from your sensor, right? So you already have data available. You don't need to wait on anything. And then you take the necessary steps for actuating, the thing that you're, the pump or whatever. Well, your processor is running probably at least several, if not tens or hundreds of megahertz, which is a lot faster than 100 hertz, right?
Right. Yeah. So you have 10 milliseconds when, if you split it all into 100, second into 100, right? You'd have 10 total milliseconds for each window. So it probably doesn't take 10 milliseconds to read a sensor.
Probably not, right? And especially if you've taken care of all of that inside of an ISR. So let's say it takes a millisecond for this thing to run. What's that task doing for the other 9 milliseconds, right?
Yeah.
Well, it's not running, right? Because it's either calling a sleep function or it's waiting on some sort of like a semaphore that's being generated by a hardware timer if you want some nice accurate, every 10 milliseconds on the dot.
Yep.
It's not doing anything. So then your other tasks are going to run. And if you don't have other tasks that run, then in the case of a non-tickless mode, your idle task is going to just sit there and check to see if it's time to bring in another task or run the scheduler. And if you're in, if you're fortunate enough to be running not fortunate enough, if you're running a tickless version of an OS, the whole chip just goes to sleep. Well, not the whole chip, but the CPU, right? And you can go into
the power,
whatever
parts, right?
Yeah, whatever, power down whatever you need to and go to sleep for a little while. So yeah, it's not running because it doesn't have anything to do. It's got nothing. Yeah. It's got nothing to do but wait. So that's the reason it doesn't run. But the second that it does, it will be running, as long as you haven't kind of screwed things up, and now all of a sudden it's got to wait for a different lower priority task.
Right.
That's holding a shared resource. That's called priority inversion, and that's not a good thing.
Right. I feel like that always gets like pushed pretty early into the conversation as well. And I'm like, well, I still don't know what priority means. And you know what I mean? Like, it's like, I need to just understand these simple things first.
Yes.
So now the vent sensor, it takes that millisecond. It's got 9 milliseconds. And so the scheduler is like, okay, well, we can go start updating the screen.
Yep.
but the screen task is going to take 30 milliseconds.
Yep.
So like what happens after that first 9 milliseconds where it's like, okay, actually I had to go back and check the event sensor again.
Yeah, so the scheduler is going to, so either the scheduler is going to run, like if you call a delay function or whatever, right? Or it will update some software timers or something like that. Or if it kind of depends on how you have it set up and how accurate you want that periodicity to be, right? Basically, there's going to be some mechanism, either a software timer that goes off or the scheduler. Well, the scheduler is controlling software timers in FreeRTOS, but you're going to have something wake up that high priority task again and say, hey, go.
Yeah.
It could be giving a semaphore from, like if you want a really high resolution, high fidelity timing to hit that, that 10 milliseconds on the dot every single time, then you probably set up a hardware timer peripheral, and that would, just give a semaphore that your high priority task is waiting for. And then, so inside of your ISR for this, this 10 millisecond repeated timer in hardware, the only job of that ISR is to just give a semaphore to this task, or there's also task notifications, and then the moment that task receives that notification or semaphore, the scheduler is going to swap it into context, and then it'll do its thing.
Yeah. Okay. That's great. Yeah. So like if I had like a slow-mo camera of a screen that's updating and it's like just rastering across for the first 9 milliseconds,
Yep.
I might see a quick pause as it's going to check the sensor again, but then it would just continue. It would effectively just continue on.
Yep. Yeah. Yeah, exactly. And the beauty of, task priorities is that that's happening all the time, no matter what. And it just, if everything is working properly, it looks like magic because things are just happening.
Yeah.
It's perceived to be in parallel.
Right. I think what's crazy to me is that this is actually what's happening on the computers we're running right now. I mean, obviously there's more threads and they actually, but
we actually have
computers do this stuff too.
Yeah, they absolutely do.
Right.
Yeah. And you have multiple processors. So that it actually is happening in parallel. And you don't have just one CPU.
Yeah. Right. But it used to be more like the embedded ones, right? I mean, like it used to be
100%. Yeah.
Single thread. Yeah.
Yeah. Yeah. But the thing that a lot of people forget is that modern microcontrollers, they can do a lot in parallel too, believe it or not, because you have a lot of power buried in these hardware peripherals, right? So you've got hardware peripherals, you've got direct memory access controllers, DMA controllers. It's not that difficult to set up all of your communication to be DMA driven. And at the end, let's say you have like a block of 12 bytes coming back from some sensor, right? And it just, that you're always going to get those same 12 bytes, and it's got sensor data in it. Well, you set up DMA with a transfer block size of 12, and whenever the DMA controller says, hey, I've collected 12 bytes, it signals some task to go look at those 12 bytes. And that entire time, the CPU wasn't worried about collecting any of the individual bytes. It was off, updating your pretty screen or whatever. So there are actual ways to get true parallel computing on a microcontroller, but it's mainly for like communication, that kind of stuff. So it's not entirely, they're not as bad as single core microcontrollers aren't as bad as they seem, I guess.
Yeah.
But
I've mentioned on past episodes recently that I've been reading about a lot of like computer history at PARC, Xerox PARC and stuff like that. And they are talking about like early computing days. And it's like, no, they're doing it. They're doing that time slicing directly. They're doing memory. They're moving memory the hard way. And it's just like, oh boy. Yeah.
Yeah.
So yeah,
we don't have to deal with any of that. It's great.
Yeah. I mean, so you said when things go right, it seems like magic, and I could totally see that. Most of my stuff does not go right the first time. So how does one troubleshoot this? Because I'd imagine it's a straightforward process for troubleshooting in RTOS.
It is free RTOS aware. So, meaning, if you pull up like a standard debugger, and now there are a lot of IDEs that have gotten this right, but years ago, your run-of-the-mill IDE, it could only look at one stack at a time. That was the processor stack, and and you could step through if you have multiple tasks. You could like step through tasks and that kind of stuff, but you couldn't like view multiple stacks at once, right? So you couldn't view the context of multiple tasks at the same time. You couldn't just hit the pause button and be like, okay, well, hey, where's my sensor task? Where's my UI task? Where's
yeah, this one's asleep. This one's asleep.
Exactly.
This one's actually running.
And you can do all of that with things like Ozone. And I think that for sure the NXP stuff has RTOS awareness. I imagine.
Ozone is the Seger debugger, is that right?
Yes, Ozone is the Seger debugger. Yep. Yeah, and I think STM32, their Cube stuff, they have RTOS awareness too now. So.
And do they have to be aware of the specific type? Like they have to kind of understand the paradigm that free RTOS is specifically, or is it just kind of a broad subject?
Because they're actually looking inside the structures, like you have task control blocks for each task and that kind of thing. So they're actually looking at all of that to obtain stack information from what I understand. So it's not just it's not, you can't use any RTOS and then all of a sudden everything is magic.
Yeah,
you have to use something that supports the RTOS that you're using specifically. Yeah, so there's that, and you can be able to hit a pause button and get some insight as to what task is currently running, which ones are in the block state. You wind up being able to dive into a stack of each task very easily. Just unwind stacks and that kind of stuff, and see local variables and all that. So you get all that for free, and then if you wind up running into really interesting problems with tasks not completing, or a task is seemingly never running, it's starved for resources, that kind of stuff. In that case, there are a couple of different products. Sager makes something called System Viewer, and it basically gives you a graphical representation of which tasks are running.
Yeah.
And their priority, and just all laid out very nicely. There's another product called Persifio Tracealizer, I believe. And
God, that's a terrible name.
Yeah. And I think
has it been around a long time? Because it sounds like a long time.
Tracealizer, I'm not sure how long. I mean, I'm trying to think. I first found out about them and.
Sorry, if you work there, I'm sorry. I have a dislike for many names of things. It's like we're letting engineers name a lot of things, and as an engineer, I'm still offended.
Yeah, likely named by an engineer.
It's fine.
On the upside, they I guess you could say that they probably didn't put a whole lot of money into the marketing department.
That's true.
They focused on.
That's right. They're not wasting money. They're pouring it back.
That's how you wind up with names like that.
That's right. Yeah.
Or it was trendy in the 90s or whatever. I don't know how.
Yeah, that's what I was really figuring.
Yeah, I have no idea. Right. But same kind of thing, and that's actually a little bit easier. It's way easier to get set up with Tracealizer than System View for free RTOS, because it's just directly. So free RTOS has all these trace hooks built into it, and you actually have to go in and you have to kind of manually patch in a bunch of stuff.
Tell what it is and that sort of thing.
For System View, but Tracealizer just kind of works out of the box, which is awesome. It's very pretty.
Yeah.
You can just see which tasks are running, which ones are interrupting others, and they give you statistics on all the tasks, how long they've been in the block state, that kind of stuff.
Yeah.
And at least with System Viewer, you can also effectively tie like a really efficient printf debug that gets automatically timestamped and cross-correlated with the real-time graphing of all this stuff. So that winds up being super helpful too. So you if you need to orient yourself, you can give yourself little printf breadcrumbs in different tasks, and then you can kind of cross correlate things temporally that way.
Yeah. So you have a really good on page, so people that are following along on page 48, which I think is chapter 2. I'm not sure. Page 48 though, you have a realistic task setup and preemptive scheduler. And like, this is what I imagine I would want most things to look like. It basically is a graphical representation. People are looking, if they're looking at this with their mind or their ears right now, they would basically see like how many times the task is run, and then like as the task gets sliced up, and then like the scheduler being part of the task as well, because it does take time. The schedule has to take time to like feel like what's next and figure that stuff out.
And when you're using these tools, this is actually like one of the views that you have, right? So this is what shows up on on page 48 is, hey, look, here's everything that ran, and here's why it couldn't run. And
yeah, exactly. And like, I think so now I'm a little confused again with priority. So priority is going up.
Yeah, this is not Cortex M priorities, which are inverted. So higher priority is more important in this world.
Okay.
Yeah.
All right.
So
that makes more sense to me.
Cortex M priorities lower is more important, but that's not the case for
yeah, because is Cortex M the one that also goes negative as well when you need to like really do crazy important stuff?
Yeah, I mean, you have like non-maskable interrupts and that kind of stuff too. So
yeah, okay.
I'm not sure.
That's confusing.
I don't know if it starts at 0 or if there's a negative number off the top of my head. But yeah. So.
Yeah. Okay. I feel like generally this graph is very useful to see here, because it's and stuff like this where it's showing like some things are, some of the bigger tasks are getting split up, and anything. So I guess people should get the book. Maybe we can screen. It looks like you have a CC attribution. Maybe we can drop this into the show notes as well.
Yeah, absolutely. All the images in the book, with the exception of one image that I got permission from ST to use of the dev board used in the book, they're all it's all Creative Commons, so you use them as you see fit.
All right. We got some art for the show now too. That's great.
Oh boy.
As long as you have attribution.
Yeah, CC by. So
yeah,
remix them. And you can even get the source. These were all done with draw.io. So,
oh, cool.
You can, it's awesome. So, it's the PNG. There's I think my personal GitHub repo has like RTOS images or something like that. So they're all in there as PNGs, and they have the embedded draw.io source inside of the image.
Okay, great. So scrolling through this book, like I said, I highly recommend this book. Scrolling through to page 98, you show a DigiKey window, and you show a bunch of STM32 parts being available. What universe is this in?
Well,
this book was written in 1995.
Bubblegum tap shoes.
He knows the code word.
So I checked yesterday, and Mauser actually had 32 of the dev boards, the Nucleo board that's used. So.
Dev boards, no chips.
I don't know.
Dev boards, you could be solder
chips, but yeah.
Right. We're just trying to get people through the content here, not not to be able to build a thing at the end.
Well, I mean, this. To be fair, this came out in 2020, but
it's true. Yeah,
that. Well, it was written in 2019. It was just like finished up. Yeah, we didn't have to
right in time for people to be locked in. Yep. Well, a lot of so you have exercises in the book. It's all based on the Nucleo F7. I remember it's got the Ethernet port on it.
Yes,
that's what is important to me.
Yes. Yeah. So you have a Nucleo F7 for all the exercises, and the cool part about that is one of the reasons for choosing that board is that you can actually that has an onboard programmer on it. Right. So an ST-Link V2, right? And you can actually go through and reflash the firmware that runs on that ST-Link and make it look like a J-Link.
Yeah.
So Sager has, and there are instructions on how to do that, both on Sager's website and, I think I probably just put a link in the actual text of the book there. But so it winds up looking like a JLink rather than an ST-Link. So you can use all the Saker tooling on like a trial basis for non-commercial kind of stuff, which is a
That's
neat
great.
feature.
And that then enables things like System View and Ozone, or
Exactly,
is it
yes.
just okay? All right. Yeah, that's nice.
Yeah.
That's
So
great.
you wind up with like this, effectively a professional grade debug setup, just with a dev board only, which is awesome.
I have a $600 Saker programmer JLink.
Yes. Yeah.
and I didn't need it apparently.
Yeah. Yep. Yeah. You don't need it. Not for this. I mean, the minute you make your
I
own
know.
board.
That's right. That's the reason
Right.
I bought it.
Yeah.
Yeah.
Yeah. Don't put dev boards into products. Don't do
That's
it.
right.
As
That's a bad
tempting
idea.
as it may be.
It's bad. It's bad. So if people are going through the book, then what should they expect to learn kind of by the end? Like, I mean, there's different chapters, there's different topics, obviously. Is it like, should someone be able to build an entire system by the end, or is it more kind of piece by piece sort
It
of thing?
depends on your background. Like there is no, so it like, I think chapter 13, that's where everything kind of gets pulled together. And there's a little project that blinks an LED. So it has USB connectivity to your computer, and it's got like this little Python UI, and it's got a couple of buttons. So the discovery board has a few LEDs on it, and you can control the brightness of each LED with little sliders on the UI, and that kind of chugs through building up this message. And there's a message receiver, and then there's a couple of different tasks that are running to control these LEDs. So if you actually follow through up to that point at least, then you can get started. That assumes, so one of the things that this doesn't do is it starts out with a code base. So I think you get like several dozen pre-configured projects and configurations inside of projects for STM Cube. So like you clone the repo, and then you just import it into STM32 Cube. It's effectively just an Eclipse IDE, right? And then all of a sudden you have access to all these examples. So if you start from any one of those examples, it's really designed so that you can play with the examples, break stuff, and see
it's totally the right way to do it.
Like how it broke. So you have this sandbox to start from. So what it doesn't do is I don't think anywhere in the text does it take you through like, okay, now open the IDE and select the Discovery F7 board and select FreeRTOS. And honestly, like that, a lot of that stuff changes so quickly that anything in print isn't going to be able to keep up with it, most likely.
I mean, even YouTube video, like I find YouTube videos, and I'm like, this tool change is completely different now.
And that's the crazy part, is that like, with a lot of this stuff, they have all these silicon manufacturers, they're coming out with all these really cool tools for configuration, but it's very difficult to use them long term. If you have a long running project that needs to be supported, you wind up either needing to kind of divorce yourself from the actual like setup portion of it and like just make an archive of the project, right? And then just deal with the actual source that matters. Because, in 5 years, you're not going to be able to like add in another GPIO line that you need to access, or reconfigure this extra this extra peripheral to do whatever task using the old project with the new IDE, right? Like it's just, it's moving too quickly. So importing source, knock on wood, that process changes much more slowly, thankfully.
Yeah.
So,
right. I think it's just then when you do need to dig through all the registers that set things up and whatever, you either need to start from a project like you were offering here, or you need to be prepared for some time with the reference manual and really making sure things are right.
And that's the strong point of a lot of these IDEs too, right? Is that they're very good. Well, some of them, NXP more so, I think. They're very good at creating like a workable starting point. But after you get that initial setup, my normal workflow is, okay, look, I've got, I know what registers to tickle. I know what bits in the registers and all that. Okay, fine. Let's bring all that in and make it, let's make
Right.
it our own, and then put an interface
Right.
on
And I'm
top
never
of it.
touching Cube again for this project, right?
Exactly. Yes. Yeah. And
Yeah.
I've
Yeah.
talked with other engineers. They're like, "Oh, how do you get Cube to play nice with your code?" I'm like, yeah, you don't. You
Yeah.
just-
Right. No, I feel, yeah, I've done the same thing. And it's like, if I'm like, okay, well, I really need to reconfigure this, whatever. It's like, start a new project with Cube,
Yeah.
make it output the stuff, and then do a diff between the two files. Just be like, oh yeah,
Yep.
that's different there.
Yeah.
Like,
Exactly.
okay.
Yeah. And then
Yeah.
if you do that enough, eventually you start finding
Hmm.
similarities, and you're like, okay, I want to change the mode of this GPIO line, for example. I do this a
Hmm.
lot. Well, you
Hmm.
can actually just create your own abstraction for it, right? And then at that point, it's now you're starting to think like a software engineer rather than a hardware engineer,
Hmm.
and like, how can I make my own life easier down the road? And
Right.
yeah, but that
Right.
kind
I
of
feel
stuff.
like that is probably the best of both worlds too, because or the best solution for people in your and sort of my scenarios, where it's just like you still have the under the hood control versus like, being handed a bunch of hardware abstraction layers and you just don't know what's happening. And you're just like, well, boy, I hope this ADC gives me a reading back when at some point, or, boy, I hope that GPIO eventually goes on.
Yeah, and some of them are terrifying because they'll depending on what you wind up with, they're doing stuff inside of interrupt. Like there's some cases where there are literally delay functions called inside of ISRs in some of this stuff.
See, I know that's bad.
Yeah, and it's I mean, you can't always avoid it if you're waiting. So if you're in a tight loop, like waiting for like the last bit of a byte to come in or whatever, right? Like, hey, you've got something in your receive buffer, or I've got something going out of my transmit buffer. Now I need to pull and wait until it's complete. Like, okay, that's one
Mhm.
thing, but finding out that you're delaying 20 milliseconds while you wait for an ADC to warm up before you take a reading, like, oh no, and you're in an ISR context. Oh geez, that's no
Yeah.
good. You can't do that.
Yeah, yeah, it just blocks it all, huh? Just hope
Yeah.
your overall system rate is less than 100 hertz.
Yeah, and yeah, exactly, and that that kind of stuff happens. So
Yeah.
yeah, beware
So
of.
like in that scenario, how do you find that then? So then you'd be like, so just to tie that back to the system viewer and the other stuff you talked about. So like you'd then see that task kind of just hanging there, or what would you see in terms of a debug?
Yeah, so like if you had all ISRs instrumented, if you added instrumentation code like enter ISR, exit ISR, then you would
Mhm.
actually see the ISR show up right on the screen, and you'd see that you're spending 30 milliseconds inside of this ISR. Barring that, you would just see like a blank spot on the screen, for example, right? And you're like, oh, well, there must be some sort of an ISR being serviced. Oh, what the heck is
Huh.
that?
Okay.
And then you can kind of go through and start poking around there.
Yeah, okay. So if you have a blank spot, right? Can you see like, well, task number 1 always runs before this blank spot. So then you might go and
Well, it
instrument
doesn't.
task number
It might
1.
not though, right? So
Oh, okay.
if you're asynchronous to that task, now this is
Oh,
where
okay.
my other favorite tool comes in. So I typically run with pretty much always at minimum some sort of a debugger, right? If you're doing a lot of this timing kind of stuff, system view or something to visualize tasks is nice for complicated troubleshooting. Certainly, good old printf is kind of nice to have for other reasons, but a logic analyzer, right? Just instrument the
Yeah.
crap out of everything significant coming off of that processor and just leave it there, right? Like the entire time you're doing system
This is a man
integration.
with extra pins on his boards, folks.
Well, no.
Okay. All right. All
If it's
right.
coming off the processor and you're going to an external chip, it's already there, right? You have a trace
Mm,
somewhere. I mean, assuming, okay,
okay.
so a lot of the stuff I work on is bigger. I can
Yeah.
afford to actually put down like a very, very tiny test point.
So you're not saying like you don't have like 16 extra GPIOs that are going out to a
No, they're
logic
not
analyzer,
extra.
but you're
Just
saying like,
instrument your external buses. That's what I'm saying.
okay,
Right.
sure.
So so if you're accessing some external chip and it's a serial bus, instrument it. And then it's amazing how much you can learn by just like taking a glance over at your logic analyzer screen. And
Mm,
you get
yeah.
it's like the pulse of the system, right? Like you
Yeah.
just glance
Yep.
over there and you see these little heartbeats because that this ADC is always accessed every 10 milliseconds. And then you know you you can start, if you have a couple of extra GPIO lines, in that case you bring those out, and then you start, you just good old GPIO toggle, right? But if you do it with a logic analyzer, then all of a sudden you have really high resolution. And if you have a problematic ISR, then you just toggle the GPIO register at the beginning, and then you know either
Yep.
do
Yep.
whatever you need to, toggles or highs and lows, whatever.
Got
You
it.
get a really clear idea of what's going on
So when
there.
you say like instrumenting the external stuff, you mean like just putting test points down or
Literally
hooks or
soldering test
whatever, like
points.
physical.
Yes.
Yeah.
Yeah.
Okay.
I'm
That makes sense.
I'm a really low level guy. So I'm not,
Mm-hmm.
you know, I have a kind of thing. I have a soldering iron at my desk. I'm not just a software guy. So,
Solid.
yeah.
Solid. Passes the amp hour test. That's good.
I once talked to somebody, and
You have chosen wisely.
we're just getting started on this project, and he's like an old school double E, and we're talking, and he's like, yeah, so what questions do you have? And I think the first thing I asked was, well, do you have a schematic? Because I hadn't. I was like, whoa! I thought you were a software guy. Like, no, I mean, yeah, I'm brought in to write software, but I need to know what the hardware
Sure.
is doing,
Yeah.
obviously.
Yeah.
Now, apparently, not
This is not
everybody
a black
thinks that
box.
way, but yeah.
Hmm. So then, okay, so now you mentioned Amazon bought FreeRTOS. They're putting more functionality in there. But then even like you also mentioned, screens are coming in. So now you need to move up the stack and do more complex stuff at third-party libraries. What does that then do for you as like this low-level person that does understand all that stuff, but then most of the processing time is kind of at the higher level functions like a screen maybe or a you know Wi-Fi connection or something like that.
And again, that's my bias towards prioritization, right? Like,
Mm-hmm.
I'm not going to say that stuff is extra, but it's less essential, right? And in some
Yeah,
cases,
yeah,
maybe it's super essential to that particular product, but
yeah. I think it's just the stuff that you've been doing for sure. It sounds like like high reliability type stuff, real things that actually need the real time piece of it.
yeah, yeah. So yeah, you just I mean, you just kind of accept it, right? And then at some point, there are always going to be trade-offs to be made. If you have that kind of glitchy feeling UI, then maybe you need to like tone down the animations or something. I don't know. There's or you know, there's a trade-off to be made, right? You either throw hardware at it or simplify it. One of the two. But
Yeah. Okay. Are you feeling the pull of the embedded Linux space as well? Like, do you feel that like either, I guess from your day to day work or your work and your
I
past
mean,
work?
I've done a few embedded Linux projects, so
Mm-hmm.
it's not something totally foreign. I mean, I like suffered through Yocto for six months getting a system on modules set up and brought up, and
uh,
in
yep.
a fully networked environment. So yeah, I mean, depending on the product, it makes a lot of sense. I'm not at all opposed to full operating systems.
Yeah.
They're great. You have a whole bunch of other people's code that you can use most of the time, and get a whole bunch of functionality that you don't need to directly create, which is awesome.
Yeah.
Yeah, in a lot of cases, what works really well is if you have very strict real-time requirements and you have a little bit of wiggle room in your BOM, just add in a microcontroller to do, the
Yep.
simple hard
Yep.
real-time stuff. And then, everything else that requires these, crazy stacks and protocols that you'd rather not look at or recreate, or you can't or whatever, run that on an OS, and then just have some sort of a serial interface between them. So
Yep.
thankfully hardware is less expensive every day. So sometimes we can solve
Yes.
problems with just more hardware every once in a while, right?
Yeah, as long as we can buy it.
Yeah, there is that. And then that's another good reason to write code that doesn't directly access your processor registers, right? Because it's probably these days it's probably going to be running on a couple of different processors.
Yeah. Yep. Exactly. So then, okay, this is the last thing I promise, because I've kept you long enough here. But so then, if you do have that coprocessor there,
Yep.
right, and it's just doing a couple small functions, that would normally have FreeRTOS as well, or would that be? I guess.
I don't
How
know.
often do you find yourself going back to Superloop then? You personally?
Me personally?
Yeah.
Whenever, if I know that something is simple enough that I'm not going to want to do anything concurrently, then sure, Superloop it is, no problem at all. It's great. The minute that, like, for new projects, I wind up, I guess the things that I create are often the projects that I'm involved with wind up being large enough that at some point it's highly desirable to have some level of concurrency.
Yep.
So, in that case, it doesn't really make a lot of sense to try to shoehorn that into a super loop if you've already got like a whole bunch of stuff that's operating well and kind of tailored towards an RTOS. There was one case in the past where we had written a lot of libraries, like some middleware kind of stuff, and we actually couldn't afford the overhead of the scheduler. That happened one time. This processor was like just totally maxed out, super tight timing constraints, and there was just no way to run an RTOS on it. But in that case, all we really did was the middleware was created in such a way that instead of a free RTOS queue, we were just using like an in-house ring buffer, for example, right? So you can kind of abstract things well enough that a lot of the code doesn't actually care what it's running on at the end of the day, right? It's just like, hey, I have data for somebody else here. I'm going to,
get your data here,
pass it over. Yeah, and that's all it is, and it hands it off, and nobody cares. Yeah. So in that case, you have something that's super fast, and that middleware can run on whatever. It could run on bare metal, it could run on an RTOS, it could run on a full operating system, as long as you're not like tying everything super, like really tight coupling between all your modules and everything, and you have consistent interfaces, you can just very fluidly move between things. That's ideal. But I'm happy to work on stuff that has super loops. It oftentimes by the end of, so I think I'm in like the industrial space most of the time.
Yep.
So a lot of our stuff has like some level of network connectivity, some level of like manufacturing test code, and like all that kind of stuff. So there's usually it's desirable to like add in other features that kind of need to operate with some level of concurrency at some point. So it just, more often than not, it makes a lot of sense. And it's not, from like a ROM and RAM perspective, FreeRTOS especially, it's pretty cheap. There isn't a ton of overhead there. Yeah. So it's not like, if you're using like a Python interpreter or something like that, where, oh yeah, look, I have this 256K ROM, and it's almost big enough for my 20-line script or whatever. I don't know how big the normal runtime environment for that is, but
it is impressive how they squeeze it down these days. But it's sizable.
Yeah.
So. Brian, where can people find out more about you, about your book, and buy your book, and hopefully try it out? And also, where can they find the boards to run? Sorry, that last one was a
bubblegum tap shoes. Bubblegum tap.
Yeah.
Well, Mauser does have, well, as of yesterday, they had 32 of them.
All right.
So,
See, he did his homework, folks. He
yeah,
checked before he came on the show. This is really nice
I
of you.
did. Well, who knows by today. But yeah, I'm probably easiest to get a hold of through LinkedIn. If you search for Brian Amos Embedded, you'll be able
Okay.
to find me. The book's on Amazon, so that's nice and easy. You could email me directly, Brian Amos at holistisembedded.com. And I've got a landing page as well, but that's not really worth mentioning. Find me on LinkedIn. You want
Yeah,
to
yeah,
chat?
yeah. Yeah, that's great. All right. Well, thanks for first off, thanks for writing this book. It was really useful for me, and thanks for coming to talk about it today. I
Thanks for having
think
me.
this helped me understand it even more. So we'll hope to chat soon.
Yeah, thank you very much, Chris.
Mutex. Semaphore.